So our next speaker is Simone WARZEL. She's a professor of analysis at Technical University in Munich. And she's a mathematical physicist who will talk about mathematical challenges and results related to fractional quantum Hall effect.
So it's actually a great pleasure to be here in Grenoble. And the topic which I picked for today's lecture, I think is particularly fitting for this location. So first of all, there's a strong group of mathematical physicists in Grenoble and Lyon. But also, there's an institution next door, which is the Institut Langevin, which relates a bit to the story which I want to tell. And the reason why it does relate is that one of the main protagonists of my story actually was working here at Institut Langevin for 5 years, and that is Duncan Haldane, just shortly before he put up the challenge on which I'll report. Okay, so as I said, I want to report about the mathematics motivated by fractional quantum Hall physics. And please do not run away if you did not study physics. One doesn't need to be a physicist to appreciate some of the beauty and mathematics which is behind this physical phenomena. Let me nevertheless start by describing the physics phenomena, which is behind what I will talk about. So if one takes a two-dimensional semiconductor in a strong perpendicular magnetic field and applies a voltage, then one sees a direct response, namely a current, and the current which builds up defines a conductivity, and this conductivity is now exhibits striking features as a function of the magnetic field. And what you see here, the direct conductivity exhibits these values and zeros. And at the same time, when there's a zero in the direct conductivity, the so-called Hall conductivity, which measures the voltage which builds up perpendicular to the current where I applied my voltage first, has a plateau structure. Now, what is striking in this phenomena is that these plateaus and the zeros are actually related to filling factors of the underlying electron gas, and these filling factors are either integer, as in 1, 2, 3, or actually rational numbers, like, for example, the last one, which is 1/3. And the challenge is to come up with a mathematical model which explains this physics phenomenon. So this physics phenomena, as I indicated here, was discovered in the 80s by Störmer and Tsui, who measured on these semiconductors, and was then more or less immediately explained by Loveland, and these characters got the Nobel Prize about 20 years later. All right, now what is a mathematical model for that? So let me start very simple and postulate that our electron gas is actually a non-interacting gas, and so the mathematics is modeled by one particle physics. So how would you model in quantum mechanics the motion of a particle which can move in a two-dimensional plane under the influence of a perpendicular magnetic field? Well, its motion is governed by a second-order partial differential operator, which is the so-called Landau operator. This is a self-adjoint operator on the Hilbert space of L2 over the plane. And many of you know what happens with the spectrum when I switch off B here, because then you should recognize this operator as just the negative Laplacian. Now, the magnetic field B changes dramatically the spectrum of this operator. For the continuous spectrum of the Laplacian is transformed into eigenvalues, which in fact are infinitely degenerate. These eigenvalues occur at multiples, namely odd integer multiples of the magnetic field strength, and the corresponding eigenspaces are infinite dimensional subspaces of the Hilbert space L2. Of particular importance for what's going on in this fractional Hall effect will be the lowest eigenspace. And this lowest eigenspace is a space of functions which up to a Gaussian weight actually are holomorphic when I identify the plane with a complex plane. So this space in mathematics is known as the Barkman space. And many of you who work maybe in wavelet analysis, and we will know these spaces because they're Hilbert spaces with reproducing kernel. So in this case, it's the simplest reproducing kernel, namely of a Gaussian weight. And what is important is, what I'm going to explain is that on this particular Hilbert space, namely the Barkman space, point evaluations are continuous. And the same is true actually for taking derivatives. Taking a derivative with respect to z, and we just is taken care of by a multiplication, as you can see from this reproducing kernel. Okay, now does this model explain what we saw on the previous slide? Well, you know, an electron gas, that's fermions. And so fermions, there's the Fermi-Pauli principle, which says that you can now occupy the eigenvalues of this one particle operator just by a single electron. And so if you think of somehow having a particular number of electrons and then cranking up your magnetic field, then since each of those Landau levels can accommodate a certain number of particles per unit length, and the unit length here in this problem is always the magnetic length L, which are abbreviated by this little l here, which is just 1 over the square root of the applied magnetic field. So if you accept that each of those Landau levels can accommodate a certain number of electrons per unit length, then if you crank up the magnetic field, you will see that, you know, for example, if it takes 2 Landau levels to accommodate all of your particles which you have at a given filling factor, but then if the magnetic field increases, all of the particles can suddenly be accommodated in the lowest Landau level. And so if a Landau level is completely filled, nothing moves, or the particles cannot move anymore, and that explains these zeros here in the direct conductivity and the plateaus corresponding to it. Now, but as you see, somehow these zeros, they occur then at filling factors which are integer. But what the fractional quantum Hall effect is about, it's about explaining those rational values. And what my talk will focus on is an explanation of, in fact, the easiest rational factor which appears here, which is the filling 1/3. Okay, now as you see from the measurements here, this 1/3 filling occurs at quite large magnetic fields. The magnetic fields here are measured in Tesla. So 30 Tesla is quite a bit, because if you think about your magnets, which you have at your refrigerators at home, they cause a magnetic field which is really a fraction of a Tesla. Okay? So these are extremely strong magnetic fields, and then it is very reasonable that at low temperatures where these experiments are performed, all the physics or the accessible states are from the lowest Landau level, that is, the physics is described, in fact, by functions in this Barkman space. All right. Now, it was Lovelin's proposal for a description of these fractional numbers to write down a many-particle wave function which now models interacting electron. And this is a many-particle wave function which now corresponds to states in the lowest Barkman space. So therefore, it has to be of the form of a Gaussian weight times an analytic function of these n variables, which now describe our n electrons. Okay, the particular wave function in which he wrote down is just a product of those Gaussians. That sounds like independent particles, times a Jastrow factor, which is given in terms of powers of the difference of the distance of two particles. Now, these powers can be integers in Loveland's description. Now, let us look at these wave functions a bit closer. If I now take this integer to be odd, then what you should immediately recognize is that these wave functions have the property that if I now exchange two particles, so if I exchange Z1 with Z2, then for an odd P, this exchange of the two coordinates results in a phase, namely in a negative sign. So these functions are antisymmetric under arbitrary particle exchange. And conversely, if P is actually an even integer, if I exchange two particles, then nothing happens in this wave function. So these are actually symmetric functions as far as particle exchange is concerned. Now we have to pause a bit and remember that fermions and electrons in the fractional quantum Hall effect are fermions. They are, in their many-particle description, described by many-particle wave functions on the n-fold tensor product of the underlying Hilbert space, which have the property of this asymmetric of being asymmetric under particle exchange. Okay, so if I'm taking an electron gas, therefore I should, if I model something like a fractional quantum Hall effect, I should actually take an odd integer here. Now, why did I call these wave functions to be wave functions of an interacting system? Well, notice the following, that only for integer p equal to 1, this function is actually a result of a totally anti-symmetrized version of powers of the odd of the monomials z to the j. And if p is other than 1, some other odd integer, like the next one would be 3, this is not any more of the form of an independent electron gas, so of what is in physics called a Slater determinant. Also, if one now takes p an even number, then, as I said, one describes bosons, and you might be puzzled now, because the fractional quantum Hall effect, that's about electrons, so why am I describing bosons? Well, as it turns out, beautiful mathematics is never wasted. These kind of wave functions play a role in describing a gas of very cold atoms which are rotating in a trap. So for p even, for example, p equal to 2, these wave functions were later discovered to describe a completely different physics phenomenon. But that's just a side remark for today's talk. Okay, so let me stick here with p odd for this talk. And what you should take away from this slide is that Loveland proposed these type of wave functions which I can modify by an arbitrary holomorphic and symmetric function. Why symmetric? Because if I multiply here a symmetric function, the overall function here for p odd will still stay antisymmetric. Okay, and that describes fermions in this particular situation of a Barkman space. And that's the description of the ground state of what's happening close to a plateau according to Loveland. Now, I wrote down here that the number p is tied with a filling factor. And if this is correct, then, for example, p equal to 3 would actually result in the description of the 1/3 filling. And yeah, okay. All right. Now, how can we understand that? So what's the filling of this many-particle wave function? Let me do the following trick and just look at the modulus squared of this many-particle wave function. The modulus squared of the many-particle wave function is a probability density over these n coordinates. And I can write this probability density in the form of a Gibbs factor, namely e to the minus an electrostatic energy times a normalization, which in physics would be called the partition function. So let us have a look at what kind of electrostatic energy is defined by taking the modulus squared of this wave function. Well, this electrostatic energy has two parts. It has the part which comes from the Gaussians of my lowest Barkman space, plus a factor which comes from the Astro factor, which I multiplied, and that gives rise to this logarithm here. Now, people who work in Coulomb gas and one-component plasma should immediately realize that this is indeed the electrostatic energy of particles with a charge minus p, which just interact via Coulomb interactions. Remember, we are now here in two space dimensions. So the Coulomb interaction is not 1/r, like what you're used to in 3 dimensions, but the Coulomb interaction is in fact the logarithm. Okay, so this part here is just the Coulomb, the electrostatic energy of point particles of charge p, which interact by usual Coulomb interaction. And how can we interpret this part? Well, just calculate the Laplacian on the function modulus of z squared, and then you see that the first factor in fact describes a uniform background, and this uniform background is a charge density which is proportional to this 1/magnetic length squared. All right, so we can reinterpret this many-particle wave function as a classical Gibbs state of a system of n-point particles with charge p in a uniform positive background. People who now work in random matrix theory will have a different interpretation for this function. If you now take the special case p equal to 1, you might or might not have seen these type of probability distributions as the joint distribution of eigenvalues of a particular random matrix ensemble, namely the simplest random matrix ensemble which you can look at, and that's just IID Gaussian entries in an n by n matrix. Okay? And it's known, it's a classical result in random matrix theory, that the joint distribution of the eigenvalues is exactly given by this Gibbs factor, which relates to the Coulomb gas description. But now, from this case, we can actually immediately answer the question, what's the one-particle density associated with this many-particle wave function? Because random matrix theory tells us that on the scale of the large system, which is square root of n, square root of the size of the particle, the density of eigenvalues which you see obey the circular law. That is to say, these eigenvalues on the scale square root of n are just uniformly distributed over a ball of radius square root of 2L squared when p is equal to 1. And the density is therefore given by that factor. And you're not supposed to be surprised by that, because if you have unit charges which are in this completely constant positive charge background density, then what these unit charges do is they just try to compensate uniformly the positive background charge. Okay, now you might say, well, that happens at p equal to 1, what about other p's? Now, if you look at these electrostatic energies very closely, you will see that everything is scale invariant. So, pulling out a factor of p basically changes the length scale by 1 over square root of p. And that's why, since you're effectively in the low temperature limit of this Coulomb gas, this result applies also for other p's. And now we have an interpretation of the fact that indeed these seemingly complicated many particle wave functions describe a gas where the filling factor is exactly given by this rational factor of 1 over p. All right. Now, you might want to object and say, well, but didn't she just tell us that I'm allowed to multiply these Loveland wave functions by an additional holomorphic function of n coordinates? Yes, you are, but still, it's a result which was proven, in fact, only very recently by Lee, Brugerie, and Ingvarsson, that at least in a weak sense, the one particle density of this modified Coulomb gas is in fact bounded by a filling factor which is 1 over p. And a kind of hand-waving description of that is the beautiful realization by these authors that, what happens if you modify by this holomorphic function is that in this electrostatic interpretation, you're adding additional negative charges. That is because as a function of each of those coordinates, the function minus log modulus of a holomorphic function is always subharmonic, and therefore what you add is effectively negative charges. And once you add negative charges to your particles, of course, by a hand-waving argument, you might agree that the system sort of spreads out more. So the one particle density should in fact decrease. Now, I should emphasize this is a hand-waving argument, and the proof, of course, is non-trivial and required subtle multi-screening estimates. And that's done sort of in their papers. All right, now that we understand the filling factor, using this Coulomb gas of random matrix analogy, let's proceed. In some sense, you might say, well, this is all kind of a bit of chemistry, because we are proposing orbitals, and that's not how physics should look like. Physics is about a microscopic description of these models. And in fact, this is where my main protagonists comes into play. These models were proposed by Haldane shortly after Loveland wrote down these wave functions. Now, the realization is the following, that you can actually describe the ground state. You can describe these Loveland wave functions, which are these Gaussians, Jastrow factor times a holomorphic function of n coordinates. You can describe them as the ground state space of a family of Hamiltonians. Okay, and these family of Hamiltonians are actually of a particularly easy form. They involve pair interactions, which are non-negative, and these pair interactions are actually given by projection operators on the two-particle space. And these projection operators have the interpretation that they project on states with a relative angular momentum p minus 2 in the lowest Landau level. Now, if you don't like this description, here is a more sort of two-particle version of writing this down. So this projection for p equal to 0 can actually be realized just as the singular interaction delta of z first particle coordinate minus z second particle coordinate. You might say, oh, well, that's a delta function, that's kind of fishy, mathematics. No, it's not, because we are on Barkman space. And remember, on Barkman space, in fact, even point evaluations are continuous. Okay, so what does this pair interaction do? Well, it enforces the many particle wave function to vanish actually upon contact. So it forces zeros in the kernel of this operator. You might say, but why does she write down a 0 squared? Well, you know, for p equal to 2, we're dealing with bosons, right? So, you know, zj minus zk to the power 1 is not allowed. Okay, so that's not accessible in the symmetric subspace. If one is talking about this p equal to 3, which is the plateau which I want to describe, then the interaction becomes even more singular, and you might become more worried. But you know, even if these sort of derivatives are continuous in Barkman space, and then these kind of interactions, once you project them on Barkman space, in the fermionic sector enforce exactly that the wave function upon contact vanishes in like a third power. And that's this Jastrow factor which we wrote down. All right. Now, so one can easily show that indeed the kernel of these models which describe just pair interaction on the lowest Landau level have the Loveland proposal in their ground states. This might be, again, not very satisfying from a microscopic point of view to some of you. And there it's very comforting to know that Seiringer and Ingwerson last year, in fact, proved that these so-called Haldane pseudopotentials, they emerge from the usual type of many-body Hamiltonian, which you learn in quantum mechanics, where you know, this gas it should be described to me by our Landau Hamiltonian. That's this H naught acting on all particles, so acting on the J's particle, plus kind of a generic short-range potential. And indeed, somehow, if you take the short-range limit, then these type of interactions emerge effectively in a gamma convergence limit on scales, depending on B, on this power P. Okay, so let me now describe to you what is the challenge related to these Haldane pseudopotentials. Now, to describe that, let me make a first observation that there's a conserved quantity for these Haldane pseudopotentials on the plane, and that's in fact the total angular momentum. The total angular momentum is just first coordinate differentiation with respect to the second coordinate minus the other way around, and if you rewrite this in my complex coordinates, it is this type of factor. Now, that is a sum over clearly a one-particle operator, and if you study what this one-particle operator does on our functions in Barkman space, then this one-particle operator really differentiates the holomorphic part of this wave function with respect to its coordinate and multiplies by z. So in this way, you can easily see that this operator has the integers as eigenvalues. Now, fixing the total angular momentum is now also a measure for the spatial extension and hence the filling factor of our wave function. That is easy to see because if you use these rules and do one integration by parts, you will see that the expected value of the total angular momentum is basically measuring the quadratic extent of the wave function. And the Loveland state, and that's sort of important to see for the next transparency, has a fixed angular momentum, which is proportional basically to the square of the particle number. That's just an exact calculation. Now, if there are any people from algebra left in the audience here, let me emphasize, because we are dealing with holomorphic functions, they're kind of hidden algebraic concepts, and one of the ways to see that is that the operator which I'm studying, namely this Haldane pseudopotential, once I fix the subspace of a fixed total angular momentum, this now fixes a attention to functions whose holomorphic part is in fact an antisymmetric polynomial of degree at most L. Okay? And that's the subspace on which I study then the spectrum of my pseudopotentials. Okay, let me provide you with kind of the bigger picture of what one expects. So here, in fact, I brought you one of the earliest numerics of the spectrum of the Haldane pseudopotentials in case of bosons. That's p equal to 2, but for fermions, things will look very similar. And for particles now, you might say, that's kind of a very lame numerics, but bear in mind, even if we are fermions, where the Fock space on which you then study the spectrum of this Hamiltonian with an arbitrary number of particles, in fact, is the dimension of it grows exponentially with the particle number. So when n is equal to 4, we've just heard that the Loveland state, which is in the kernel of this operator, so that's 0 here, realizes this point, which is 12 in the kernel. It's the total angular momentum 12. Now what you can see is sort of from the spectrum, if I now sort of increase the particle number and then also sort of increase the momentum, is that the Loveland state which sits here is the state with a property that it is the state which has the smallest angular momentum in the kernel. Okay. If you then go to smaller angular momentum and ask what's the spectrum, you will see that the ground state actually increases with decreasing angular momentum. So this is a spectral rigidity which is inherent to all of these pseudopotentials, supposedly. Now, what is very important in this graph is what you can see here is that the ground state, which is inherently at 0 energy, is separated by a spectral gap from the excited states, which occur on the orthogonal complement of the Loveland states. And the spectral gap is in fact uniform in N and L. And that's exactly Haldane's spectral gap conjecture. Okay? So why is the spectral gap conjecture sort of particular importance? Well, first of all, if you prove this spectral gap, and that's the spectral gap which is uniform in N and the total angular momentum, you've actually proved one characterizing features of these fractional quantum Hall systems, and that's their incompressibility. Because see, if I now sort of try to compress the system, it means I'm trying to reduce my angular momentum. Remember, angular momentum is a measure for the filling factor, as I've just explained. Then I can compress only up to the Loveland state, and from there on, we have to actually pay a price of an energy. And that's a robust energy, and that's this incompressibility of this fluid. On the other hand, if you prove spectral gaps, it's also an indication that the phase of matter, which is described to me in terms of this Loveland proposal, is in fact a stable, good phase of matter, which is stable under perturbation. That's something which we expect in physics. Okay, so that's why there's a big deal made in physics for proving actually that the spectral gaps occur in these pseudopotentials. Now, why is that kind of a hard question, a mathematically hard question? So let me put this a bit in context. Now, we are here in a many-body system, and establishing spectral gap in many-body context is a notoriously hard question. So, some of you might know part of these highlights. So, for example, in the context of quantum spin systems, one of the very known systems in mathematical physics which exhibit a spectral gap is the famous Aklt model. The Aklt model is a model where on each lattice side, and that's a one-dimensional lattice, you have a so-called spin 1 sitting. And the interaction is among neighbors of these lattices. And what you do is you use a projection interaction, and this is the orthogonal projection onto the spin 2 subspace of two spin 1 particles. So in some sort of vague form, this Aklt interaction looks very much like the Aklt, the Haldane pseudopotential interaction. It's also a projection interaction. Now, this model is in fact related to another one of Haldane's favorite conjectures, and that's if you want, the big Haldane conjecture. Namely, that's the fact that Haldane used theoretical physics arguments to postulate that in these integer spin systems, once you have a so-called antiferromagnetic interaction, and that's kind of a toy model of an antiferromagnetic interaction, there's a spectral gap in these spin systems, and this spectral gap corresponds to the topological phase, which is now known as the Haldane phase for these spin systems, and that's in fact the Nobel Prize for Haldane, which was awarded just 6 years ago. Okay, now in this particular Aklt model, one could actually prove a spectral gap, and that was done already in the 80s by Affleck, Kennedy, Lieb, and Terzaghi. Other contexts where spectral gap show up is in models of convergence to equilibrium, like Glauber dynamics or Kawasaki dynamics, or a model which looks very much again like our fractional quantum Hall system, namely the pseudopotential. That's the Katz-Master equation. Let me not describe in detail what the Katz-Master equation is. So roughly speaking, what you have is you have n particles which live on the line, and you describe their velocities. And because of energy conservation, the velocities live on a ball. So without loss of generality, and we just take a unit ball in n space dimensions. And then you describe collisions upon particle contact, and Katz's proposal was that the collision should just occur by rotating the 2 vector which is formed by the velocities of the particle j and particle k, and you rotate by a uniform angle. Okay, so this defines again a projection, and it projects now basically on a state which is constant as a function of the velocities on the sphere. And this many particle operator, so to say, is also known to have a spectral gap. That was proven in important papers by Jan Vreze and also later in a different proof by Carlin, Carvalho, and Loss. And what they made possible is the observation that uniformly in n, this operator here on this many particle L2 space does indeed have a gap corresponding to fast equilibration in the Katz-Master equation. Now, what do these problems all have in common? Well, what we're dealing with is pair potentials which are non-negative. And these pair potentials which are non-negative lead to Hamiltonians which are frustration-free. And in this frustration-free situation, there's a technique which is now known as the Martingale Method, which is an inductive technique, which I'll describe on the next slide. Now, this is not the only gap estimation technique which we have. There's a finite volume method, which also works for frustration-free quantum spin systems. But there's really not much else which allows one to prove spectral gaps in the many particle situations. Sometimes for special systems which are not frustration-free, you can employ stochastic representation and conclude spectral gaps in this situation. But that's not a method which is very robust. So let me briefly flash up the robust method. So that's this Martingale method. As I said, it's an inductive control on the spectral gap of a family of frustration-free Hamiltonians. Frustration-free in particular implies that the operators here, which I sum up, are actually non-negative. And they each have a spectral gap. So an example for an HK would in fact be a spectral projection. Okay? Then gamma here, the gap is 1, and GK, which is the projection onto the kernel, just projects onto the kernel of this particular projection. The trick is to define a family of orthogonal projections which induce a decomposition of these Hilbert spaces which I'm working with. Now, and the way this works is as follows. So you consider this as a function of n, and for each n, you have a ground state space. What is this ground state space? Well, because things are frustration-free, the ground state space for n is just the intersection of the kernels of these little entities which I'm summing up. Okay? So this defines a projection on the n-particle space, even if little n is not already big N. Now, En, so to say, takes into account that what I'm defining here is a nested function of ground state spaces, and En is the excited space of excitations which I will see kind of on the last bit of what I added. Okay, because it's the difference of the ground state space of the system of size n minus the ground state space of the system of size n plus 1. If I add another positive term, of course the ground state space might get depleted because vectors which are previously in the ground state space of these n terms are not anymore in the ground state space with n plus 1 terms. Okay, because I'm adding a positive operator. And the Martingale method now postulates that if I'm in a situation where this excitation space in fact commutes with what I'm adding, at least if I'm sufficiently far away, that's this L which I have here, and that upon one step addition, what I'm adding as a ground state space is sufficiently orthogonal to the excited space. Okay, sufficiently orthogonal, meaning that this epsilon is sufficiently small, namely 1 over square root of n, so that the estimate which comes out here at all makes sense. And this is a theorem whose present form was proven by Bruno Nachtergaele in the 90s, and which has a long history going back, in fact, to the famous AKLT paper, which I mentioned, and also to applications in these Glauber dynamics by Lu and Yao and in the Katz master equation. I should also say that the HKs which in application you use are not the individual entries, but what you might want to do is you might want to add a few of those projections and define an effective HK to get a good estimate here. All right, but that's kind of a very robust technique, which at least for short-range models where you have this commutation property, once you wait long enough, you can apply. Okay, so much for this interlude. No? Okay, now let me come back sort of to the challenge. I worked on the plane and described this Haldane spectral gap conjecture on the plane. In fact, there's a footnote to the spectral gap conjecture, that the spectral gap, in fact, doesn't really depend on the two-dimensional geometry which you have in mind. So instead of taking a plane and a perpendicular magnetic field, you could as well take a sphere and a perpendicular magnetic field, or the torus. Let me, in fact, describe the situation on the torus, or more precisely, the cylinder geometry. Now, of course, our Barkman space changes now. So what is the one particle space on the torus? Well, here's an orthonormal basis, and that's a particularly convenient orthonormal basis. It consists of functions which are Gaussian weight with respect to the longitudinal coordinate xi in our cylinder. So that's the xi coordinate, and it has a phase with respect to the other coordinate, which is the angle coordinate. Now, in a cylinder geometry is then characterized by two lengths. We have the magnetic length, that's this L, which defines our orbitals, and we also have the radius of the cylinder. And the ratio here describes the particular geometry, or kind of the size of the cylinder geometry. Now, if I take alpha very large, then what happens to these Landau orbitals is they get very much spaced in between. Also note that effectively how I now describe the Barkman space is as a quantum lattice systems, because then I have orbitals which are associated to integers, describing the coordinates of my orbitals along my cylinder geometry. And if I now take my favorite Haldane pseudopotential, then this pseudopotential can be rewritten in second quantized form, maybe because I'm not fixing the number of particles. As you saw, the spectral gap conjecture is about uniformity in the particle number. So I'm expressing everything here in terms of creation and annihilation operators associated with these Landau orbitals. And you can write this Haldane pseudopotential as a fourth order operator in terms of these creation and annihilation operators. The way this works is there's a sum over half integers of the lattice, and the second sum which enters here is either also over half integers, making sure that the combination here is again an integer, or an integer depending whether s was integer or half integer. Okay. You can figure out what these prefactors here are. These prefactors are given by Gaussians, or Gaussians modified by t, or another Hermite polynomial for the other filling fractions. All right. Now, what I now want to do is I want to cheat a bit, because this is a long-range model. As you see, somehow with the terms which appear here, we have arbitrary hopping range. But if I'm in the thin cylinder limit, which is alpha going to 0, then my Gaussians here become fast very small. And therefore, physicists have suggested to truncate these k-sums at the lowest non-trivial terms. And in case of my 1/3 filling, this is actually k less or equal than one lattice spacing apart. Okay. Then the type of operator which I'll end up with in a truncated situation, describing this 1/3 filling, is the following quantum lattice operator of fermions on this lattice defined by these orbitals. So X is an orbital in my Barkman space. And this has two terms. One is, so to say, trivial, because it's a complete electrostatic term. It gives energy to those configurations where a particle sits at X and another particle sits two lattice sides apart. And there's a non-trivial term, which is a hopping term. And this hopping does the following. It takes two particles which sit next to each other, here marked in red in terms of these orbitals, and moves them to locations which is 3 apart. So it does approximately that. Okay, that's the type of hopping which you get. Okay, so we move from particles which sit next to each other to particles which sit three apart. Okay. The type of hopping is not the regular hopping which you know from your Hubbard models or so. That's actually a center of mass preserving hopping. But the center of mass plays the role of angular momentum in the planar geometry. So that's our conserved quantity. Okay. Now let's go through what we can prove in this situation. What of course we want to investigate is finite volume versions of these lattice operators, and we will just truncate and restrict my attention to orbitals which are about living in this interval A, B, and everything is defined in Fock space. All right. Now, let me be very brief for my second part, and that's just really the last 10 minutes. As it turns out, this type of lattice model can be described completely, and you can prove Haldane's challenge, at least for this truncated model. And the reason why you can prove this is, remember, spectral gap questions are the challenge of solving a variational problem orthogonal to a ground state manifold. Now, the Martingale method gives you a way to inductively control these spectral gaps by making the system larger and larger. But what you have to estimate in this Martingale method is you have to still estimate orthogonal complements with respect to increasing ground state manifolds. So it's very important that you understand the ground state manifold. As it turns out, in this truncated model, the ground state manifold has a beautiful description in terms of dominoes. And that's a joint work with Bruno Nachtergelle and Amanda Young, which I want to report on in my last 10 minutes, and more will be said this afternoon by Amanda. So let me just briefly go through describing how you construct this ground state. So see, if we take this model, then let's start with the simplest case where there is no hopping, where what we have is just a completely electrostatic problem. How would the ground state of this electrostatic problem look like? Well, you prevent particles from sitting next to each other, and you prevent particles from sitting 2 apart. So the only thing which you can accommodate is a particle configuration which sits 3 apart or further apart. And then there's something nasty happening at the boundaries, which results from the fact that I didn't include all terms here. Okay, so in this situation where lambda is equal to 0, that's a ground state. And now you can see the maximal filling which you get is clearly a third filling. That is when you exclude these 0 dominoes. 0 indicates there's no particle sitting here. 1 indicates there's a particle sitting here on this orbital. Okay? Just by inspection, these things are at most a third filled. Now what happens if I turn on lambda? Well, then of course, this is not anymore an eigenstate which I'm symbolically writing down. But the type of substitution rules which are suggested by the center of mass preserving hopping is the following, that in order to get a ground state, you have to include further dominoes in your description. What kind of dominoes? Well, if you have 2 monomers sitting next to each other, they can hop and form a dimer. And this can occur all over the place. So this now defines equivalence classes of dimer coverings of my orbital part, which I'm trying to describe. So this is this length AB. And all of these dimer coverings result from a root tiling, which is just coming from this electrostatic description. So in this way, I can define subspaces of my full many particle space, and that's these tiling spaces. the tiling spaces work as follows, and I take a root tiling, and then just take sort of all the tilings which result from this root tiling by substitution of monomers with dimers. Okay, so this defines obviously an orthogonal decomposition of subspaces which are consistent with a root tiling. It's not my full Hilbert space, but it's a subspace. Now, the important thing to realize is that the states which you can form from these tiling configurations, where I linearly combine states for a given root tiling in such a way that I respect all the substitution rules, and for each substitution rule I get a factor of lambda whenever I see a dimer. This can then be proven to be a unique ground state in this particular subspace corresponding to a root tiling. And in fact, the full ground state space of my Hamiltonian is in fact described by all of these states with the different root tilings which you can come up with. So that's just placing monomers or zeros or boundary dominoes on the on my segment which I want to describe. As I said, all of these states have the property that they are at most maximally a third filled. That's just by inspection, and the proof is by simple combinatorics. Now, what we also see is something which you have in common with the original Haldane model, which I showed to you, is that this ground state space is vast. In fact, it grows exponentially with the system size. Okay. Now, so each of those states corresponds to one of those domino tilings and their substitutions. And one can now ask sort of different properties of these states. So one of the properties which is particularly fancy in theoretical physics is to ask about the entanglement structure. So that is encoded in the Schmidt rank of any bipartition. And it's very easy to see that the reduced density matrix to such a state which corresponds to a domino tiling has at most Schmidt rank 2. So it's a, so to say, a particularly simple and non-entangled state which sits in these ground state spaces. In fact, it is a fragmented matrix product state because, as long as you have zeros, states factorize, so there's no entanglement. But on the remainder, what you can form is these type of states, and they result in this Schmidt rank 2, and one can easily convince oneself that they actually form what is in physics known as matrix product states. And they are the fundamental building blocks to describe this full ground state manifold. Now let me conclude, let me skip this here, and let me conclude somehow with a remark on the spectral gap. So see, what one wants to prove in this case is that there's kind of a robust spectral gap. And the conjecture for these models is that it's really robust in lambda. But if you're taking these type of Hamiltonians with open boundary conditions, maybe you just cut the cylinder, one can easily convince oneself that the spectral gap is not robust as a function of lambda. In fact, that's something which we can prove. There is a spectral gap, but the spectral gap for these open boundary conditions is uniform in particle number and the system size, but it closes with lambda squared as the hopping is switched on. If you, however, go to a torus geometry, where you can similarly define things, then indeed Haldane's spectral gap conjecture is now proved in this truncated model. One can prove that the first excited state is really robustly bounded away when lambda goes to 0. Now there's this function f, which I plotted here. Don't look at the details. That's basically sort of the result which we proved in the last 2 years. How did we prove it? Well, in some sense, what we did is we adapted with the Martingale method. We combined it with finite volume criteria, which I didn't talk about. And one of the adaptations which was necessary is that's known in this people who deal with spectral gaps is that the Martingale method, of course, uses information on the open boundary Hamiltonian. But if the open boundary Hamiltonian has a gap which closes with respect to a parameter, you cannot hope to prove any robustness with respect to this parameter. So I have to do something else, and there's a method of reducing subspaces which Amanda will explain in more detail in session 10 this afternoon. So let me close with that. No? That's not going to work, but let me skip the excited stage. So let me close with that. So I hope that I convinced you that there's interesting mathematics, non-trivial mathematics in this question of spectral gaps in describing these Loveland phases. At least for the truncated Haldane potential, these conjectures are now fully proved. And the challenge now, that's a challenge to all of you, is to face the complete conjecture and prove the same type of estimates for the untruncated Haldane pseudopotentials. That can be done maybe in two ways. Namely, you might want to prove stability of the estimates with respect to adding different terms, or you might if you want to employ a completely different method. Let me say that as you see, there's an algebraic structure which is hidden in all of these problems, and that you saw in this description by Dominos. It's a combinatorial description of the ground states. There's a similar combinatorial description which is hidden in so-called Jack polynomials for the full problem. And if you have an idea how to effectively describe this monstrous ground state manifold for the complete Haldane potential, you might have a chance in actually establishing this important physics conjecture. There's more to be said about these fractional quantum Hall situations. In fact, as maybe the physicists in the audience know, the excitations that have are conjectured to have a particular structure. They're neither fermions nor bosons. They have an anion nature. They have a third fractional charge, which you can sort of see from the description in these dominos. And you might also ask what's happening at other filling factors, which are not 1/3, 1/5. Well, there's a different theory which, after you solve this problem, you can then face. And I should also say, these type of truncated pseudopotentials, they define a phase of matter which physicists now investigate quite a lot. That's this fractonic quantum matter. And once we understood how these spectral gaps can be proven, you might actually employ these type of techniques to prove other spectral gaps in fractonic systems. Fractonic systems are systems where the hopping in a quantum lattice model is not in this translation invariant way, but it respects dipole moments or further higher multipole moments. So there are blockages, and this is usually resulting in gapped phases of matter. So, as I said, I hope I could convince you to join working on this exciting field in mathematical physics. What I only briefly mentioned at the very beginning is that it connects me to this beautiful mathematics of the one-component plasma and Coulomb gas model. That's something which where more can be said, and if you're interested in, I would refer you to beautiful articles by Nicolas Rougerie summarizing the story. And if you're enticed in joining the quest of establishing Haldane's little conjecture and not Haldane's big conjecture, which is related to the Heisenberg antiferromagnet, this is maybe a starting point where you could join the show. Thank you very much.
Thank you, Simone. So, are there questions or remarks from the audience?
Simone?
Oh, couldn't see.
Yeah, thank you for this nice talk. I have a basic question, which is that I understand the integer quantum Hall effect a bit better, I guess. And there, the understanding is, to my experience, very different in the sense, well, there's actually much more general understanding in the sense that once you talk there about a band, you have something like the Chern number. And once that Chern number is non-zero, you can conclude that there is sort of an integer quantum Hall effect, which is very nice and very general. So here, it seems very different in the sense that one studies, well, just the lowest Landau level. Then one imposes some sort of Coulomb interaction, but actually, since one doesn't know the ground state there, one comes up with these Haldane pseudo-potentials, if I understand it correctly. And even then, so I think what I'm asking is, for a general system, if I know something about, so is it true that if I know something about a single particle wave function, I build up this Laughlin state, can I then conclude that there is actually a fractional quantum Hall effect? Because I never see sort of a formula for conductivity or anything like that. Or
yes.
Is that related to the spectral gap conjecture?
Okay, so the fact somehow that the direct conductivity vanishes is related to the spectral gap. In the same way as kind of an intuitive explanation of in the integer quantum Hall effect where you have the spectral gap, which is just the spectral gap of this one particle Hamiltonian, which causes the zero direct conductivity. Now, I indeed somehow, so as you mentioned, what I also glanced over a bit, there's beautiful mathematics hidden in the integer quantum Hall effect, which is much more general than this Landau Hamiltonian, which I mentioned, and relates to characterizing these phases of matter in terms of topological quantities. For the fractional quantum Hall effect, this should characterize as a phase of matter, but things are much less clear. So maybe there is a good a quantity which you can relate to a topological property. I doubt it a bit because these ground state spaces of these Haldane pseudopotentials. So one of the mind-boggling things which you face here is that the ground state space is so vast. And that might make things sort of a bit different. To your question, why did I only consider an interacting part? Because the kinetics of these particles, that's fixed once I'm in the lowest Landau level. The kinetic energy is just fixed at B. So I can throw it away. As far as Coulomb potentials are concerned, it's okay. So it's a good question, and actually papers by Rougerie and co-authors face this at least on the level of the Coulomb gas. In which sense this Laughlin phase is stable if I now have a less singular pair interaction. All of this is also not clear. Or requires a proof. I would say sort of from the point of view of physics, it's kind of clear that the experiments are justified in terms of these wave functions, and these wave functions clearly correspond only to the singular part of the interaction. And the rest should. This phase of matter should be stable, also in this sense, that you add some non-singular part of the interaction, you also get sort of you stay in the same phase. But you're invited to join the quest of proving all that.
All right. Yes, another one here.
I'm a bit confused about this enormous ground state degeneracy you mentioned. I thought the expectation was that the fractional Hall liquid has a definite finite ground state degeneracy on the torus.
Yes. So this might be sort of a bit confusing to people who in particular know papers where one describes that once you have a gap and a unique ground state, you actually have a topological description. That's sort of largely due to your papers jointly with Wojciech de Röck and Fraas. The interpretation of sort of connecting me to this part of the story is that it's actually best described in sort of in this domino tiling sense. What the states in the ground state, other than the Loveland state, represent is in fact a situation where this fractional quantum Hall fluid is fragmented. So it's not the maximally compact situation. The maximally compact situation is unique. In the other ones, physicists sometimes actually refer already to edge states because it corresponds to taking part of this fractional Hall liquid, spreading it out. That's adding zeros in the domino description. Yes, yes. So in this domino description, you have several droplets of fractional Hall liquids. That's a feature of these Haldane pseudopotentials. That's why physicists sometimes refer to these type of things, which are in the ground state, in fact already as edge states. Well, it's a feature.
Can I just suggest that we postpone the end of the answer and the end of the questions to the break? We shall reconvene at 11, and we can thank Simone again.